Hi everyone, my name is Freshte. I'm in the Office of Applied Research, and today I'm going to talk about biases in machine learning cycle. As you may all know, there are different steps when we decide to deploy a machine learning model. It starts from the business need, where there is a need and we decide to address this need with machine learning model. And then it goes through problem formulation, data collection, algorithm selection, training, testing, deployment, and feedback loops. In this talk, we are going to talk how biases, different sources of biases can creep into machine learning cycle. I mostly focus on data collection and algorithms and feedback loop, which is my expertise. But for the sake of completeness, I go through other steps as well. So let's start with business need. In business needs, the things that we should be very considerate about is developer biases. When you decide to address some needs, we should all be careful that if we are only addressing needs of a particular group, or we only causing harm to a particular group. As an example, let's consider Microsoft Teams. You might add a lot of features, which would be great for the tech-savvy people, but on the other hand, more feature can cause harms for low bandwidth network. So there is this trade-off that people should make a decision. The second step is problem formulation. In problem formulation, we should care about proxies and misuse. So whenever you have a machine learning model, usually you define a set of features and you want to predict a target. However, you usually don't have access to the true need. And instead, you use some proxy instead of the true need. These proxies might adversely affect a particular group. Let's look at some example. If the true need is if the recommendation is relevant or not, you don't have access to the true need, you are going to use some proxy. Let's say you look at the fact that if the user click on the recommendation or not. And now we can ask this question of who can get hurt because of this proxy. And we can, for example, say that people who are prone to clickbait can be harmed because of this proxy. As another example, let's look at when the true need is the previous interest of the user. The proxy can be history of the content. And the people who would get hurt is people who share the same computer with each other. The second thing is misuse. Misuse, whenever we formulate a problem, we should be considering that if this problem formulation can be applied to unintended use cases, which might harm some groups. An application that it's like really perfect for task 8 might be very harmful for task B. Now let's look at data. Data, as we all know, is one of the big components of machine learning, but machine learning models learn patterns from previously collected data. But this data usually reflect the long-standing discrimination against protected groups. I don't think that I need to go through all the discrimination that's previously applied to protected groups, but just to give you some example, for the long time, people could not vote just because of their sex, or people were enslaved just because of their race, or people get fired just because of their sexuality. And these biases in the data, they show some patterns, and machine learning is going to learn these patterns. We are going to look at 4 different biases: label bias, feature bias, distribution bias, and sampling bias. First, let's look at label bias. Label bias happens when labels are biased toward one group. As an example, let's say you want to have a model that predicts if the person should get hired or not. And you are going to look at the historical data. But in historical data, it is possible that there were some qualified women who have not been hired, not because they were qualified, but because there were some discrimination against them. So the fact that you use the label, if the person has been hired or he's been rejected, might be biased toward one group. Another example is, let's say we want to have a model that predict if the person is going to reoffend a crime or not. And then it's been shown that the white majority neighborhood, there are usually less police in them comparing to a non-white majority neighborhoods. And because of that, it's possible that some white people, they have done a crime, but they haven't been arrested. So the label 0 for them can actually be biased, and the label should have been 1 in comparing to like other groups. And then this can happen in like a less worse application. For example, let's say that you look at scoring in a Microsoft application, and then different countries have different norms of how to score. And then, as you can see, the labels can be biased toward one group than the other. The second bias that I want to talk about is feature bias. Feature bias means that even at the feature level, it's possible that the features are biased toward one group. Again, going back to a model that wants to predict if a person would reoffend or not. For this model, the number of previous arrests is actually a very predictive feature to predict if the person is going to reoffend or not. But number of previous arrests are biased against racial minority. It's been shown that for the same amount of illegal drug, it's more possible that the racial minority get arrested in comparing to whites. The third bias that we are going to talk to is distribution bias. Because of the historical discrimination, historical discrimination creates a gap between the distribution of different groups. For example, here I'm showing that the number of men and women in US Congress. And then as you can see, there were this like very, very big gap, like for the longest time, women couldn't even vote. And then it's getting better over time, but there is still the gap between them. So there is this artificial gap between the distribution of men and women. Another example, of course, this is not specific to US. You can see the number of countries where the highest position is held by women. And then as you can see, it starts from like almost 0. It's increasing, but it's not like the trend has not stopped yet. For the distribution bias, I'm going to get a bit, do a closer look and then see how distribution bias can cause discrimination. For this, I'm going to go through a very easy example. Let's assume there is a company who wants to hire people who are qualified. A person is qualified if their skill level is greater than 0, and they are not qualified if their skill level is less than 0. For simplicity, let's assume that the distribution of skill level between people is a Gaussian with average mu and variance sigma. The company, of course, does not have access to the skill level of people. So what it does is just to, let's say, either interview or either take an exam. And then for a person with skill level 0, if we take an exam, then the score would be a noisy version of the skill level. So here, the skill level 0, if we take an exam, the distribution of the score would be like a Gaussian around Z0. With some standard deviation noise, here I show sigma noise. So going back to the company want to understand what cutoff threshold it should use for hiring. To recap, the company is interested to hire people whose skill level is greater than 0, but it doesn't have access to the skill level. It only have access to their score. Let's look at two extreme cases. If first case, let's assume that there is no noise. If there is no noise, then what it should happen is that the score is actually showing the skill level. So if a score greater than 0, then the company should hire. If the score is less than 0, then the company should not hire. Now let's look at a very extreme case, when the noise is infinite. So the score actually doesn't give us any information. So what the company should do in this case, it should look at the average skill level of the population. If the average skill level is greater than 0, then they should hire everyone. And then if the average skill level is less than 0, they should not hire anyone. In general, noise is something between 0 and infinite. And then if you write down the optimal threshold for the company in order to maximize the number of qualified people, is this number. And as you can see, this number is inversely correlated to the average skill level of the group. So let's see why this correlation can cause discrimination. Let's assume that we actually have two groups, blue people and red people. And imagine that due to previous historical discrimination, there is an artificial divergence between the skill level of blue and red people. So as we discussed, the company wants to hire these people, and then it takes an exam. Exam is noisy version of the skill level, and then the optimal threshold is actually inversely related to the average score. So if I calculate the threshold, I would have some threshold like this, where the blue threshold is actually larger than the red threshold. So here it is kind of interesting that we are kind of doing double discrimination. At first, we did some discrimination, and then there were artificial divergence between blue people and red people. And now, because of we want to just find the optimal threshold, we have a higher threshold for blue people versus red people to get to hire people. So blue people have been have been discriminated first, and they are in a group that have lower skill level, and now they should even try harder to get hired. For more information about this simple example, you can look at this blog post in Stanford AI Lab, Blue People versus Nay City. Okay, so we're done with distribution bias. The first one that we are going to talk about is sampling bias. So sampling bias happens when our data is only available or sampled from some groups, or data is misrepresenting some groups. So misrepresentation, underrepresentation, erasure, these are all happening because of the sampling bias. As an example, let's consider that we want to understand if a sentence is toxic or not. Let's say we use Reddit comments to understand what is toxic or not. And unfortunately, because there are many hate speech against homosexual people and against Muslim people, machine learning learned this pattern that maybe gay and Muslim are toxic as well. So if I write for a machine learning model that it's been trained on Reddit, if I write like some people are gay, the toxicity score is higher than when I say some people are straight. Similarly, some people are Muslim is more toxic than some people are Christian. Sampling bias happens everywhere. For example, these like large language models that it's the backbone of many NLP models. They use text in internet. And then here it shows that the penetration of internet in different countries. And then as you can see, like the Western countries, around like 90% of people are using internet, but in African, Middle Eastern countries, you can see that the internet usage is very low. Similarly, we all use like Wikipedia is a big source of data for any NLP model. And then again, if you look at the demographics, it's very different from the demographic of the world population. There is majority male, majority no children, majority no partner, age between 18 and 30, and they have a higher education. So we're done with data, and then like whenever you use some data, it's good to go through all these sorts of biases and then see if they exist and what you can do about them. Now we are going to discuss about algorithm selection and training. We are going through 5 different biases that can creep into our ML model. The first one, which is like very well known, is majority bias. ML model by definition usually work very good for groups that represent the majority of data. The generalization bounds that exist for ML models, and also the way that we train model, the average loss minimization, these are all good for the majority. The second one is simplicity bias. So models usually like to learn very simple patterns. For example, in the left, if you want to classify pictures that have 0 and car versus pictures that have number 1 and truck, the model would learn only the top part of the picture and completely ignore the bottom. So it learned some very simple discriminator and it's only used that. Or in the right, it's been shown that if you have just pattern, like here, it's predict with high confidence, it's an elephant. In the middle, when you have the right shape and right pattern, it predicts a cat. But if you have a cat with a pattern of elephant, machine learning models usually like to look at the patterns. So they predict elephant. And in general, there are many inductive, implicit, unknown biases that we still don't know why machine learning doing that. And it's good to do some post-processing after you finish your model to see what is happening. For example, CLIP, which is like a very well-known combination of image and text. If you go into it, there is this like great paper that look at different neurons and then see which images activate these neurons the most. And then they show that there is this like one neuron that get activated either with Arab cloth or with mice. And it's not even clear that why this is happening, what would be the effect in the downstream application. And then it's like very different from the biases that humans have. So these like inductive, implicit, unknown biases is also something that we should all care about. This is also like a very well-known phenomena, adversarial examples, when they start from like a picture, like panda, they add noise to it, and then machine learning predict like completely different class. For example, here, gibbon, with very high confidence. So humans in general use different features for classification than machine learning. So we should be careful on what is being used and then how does it would affect different groups. Okay, let's now talk about bias amplification. You probably all have heard of, oh, data is biased, so of course this bias would show up in the model. But surprisingly, people have shown that even if you have some bias in the data, it might over-amplify with your model. For example, here, let's say that for 90% of the pictures of snowboarding are males. And then when the model predict is actually amplify this, and then it predict almost 100% of the picture of a snowboard is accompanied by a man. And then you can see similar things here. And then going back to the famous CEO example, let's say that 20% of women are CEO, but like the model can amplify this. And then when want to like generate picture of the CEOs, instead of 20% women might amplify and only show 2% women. This paper is great, and then the name is like balanced data set are not enough to show that how models not only use the bias, but also amplify it. The last one is the misspecification. If you use a very simple family model, it's possible that the true function is not in the family model, and it might affect different groups differently, as different groups might have different functions. So with this, we finish the biases in the algorithm and training. We go through majority bias, simplicity bias, the uninterpretability and things that can happen because of it, bias amplification, and misspecification. Now I'm going to talk about testing. So for testing, the first thing is the metrics that we are using, what these metrics are representing. Usually the metrics that are used for evaluation might not represent some groups. For example, the well-known average accuracy might ignore performance of small groups. The second thing to think about is user-based bias. So whatever evaluation metric that you have, it is computed based on the user base of the model, which can be very skewed toward one group. And then the second thing is that in industry, we usually evaluate our model through different rings. Therefore, some groups' evaluation enter the system faster than the other. For example, we first see the performance of our model in Microsoft, and demographic of the Microsoft is very different from the demographic of the whole population. Okay, so we're done with testing. Let's now look at questions that we should think about in deployment, which is who's the deployment population and what is the deployed task. So we should think about, are we deploying our model on a population that we did not collect data from? Are we considering the change in the population over time? And is our model deployed on a task that is not trained for? Okay, we start from business need. We went through problem formulation, data, algorithm, testing, deployment. Let's now talk about feedback loop. So whatever model that you have, it would change the human behavior. And then as humans' behavior change, the model adapt itself, and then it go through these loops. So these feedback loops can exacerbate bias and lead to long-standing discrimination that cannot get fixed very easily. So it's really important to think about this feedback loop before it becomes too late. Let's first talk about how humans change according to the model decision. So the first one is that models can alter human behavior explicitly. For example, there are some work that they show that if a recommendation system keeps suggesting junk food to a person, it might actually change the behavior of the person and their food choices. Another example is that if your model cause a person to go through some training, then of course it changed the skill level. For example, if you have a model that is going to decide if a person should qualify to join the soccer team or not, then when the person joined the soccer team, it changed their skill level. As an example for this, there is this relative birth effect, which they look at months of birth of different population, and then the orange or pink, the pinky orange color shows that the months of birth is actually uniform among general population. But when they look at the soccer team members, they saw that actually the probability of them being born in the first 3 months, like January, February, March, is higher than them being born in like October, November, December. So if you are 25 years old, then before that, when they want to decide the age of a person, the cutoff threshold is January. So if you are like 25 years old, it doesn't matter if you are 25 and 11 months or 25. But when you are very young, like 5 years old, then 5 years old versus 5 years and 11 months is actually very different. So because of the cutoff threshold is good for people who've been born on the first few months of the year, it's more probable for them to get selected. And then when they get selected in young age, their skill level increases. And then the next year, it's more probable to get selected again. And then we see that this feedback loop is happening and then cause these skews toward the months of birth, which should not have any effect on the ability to play soccer. Another way for human change is that the model actually changed the incentives for individual. Let's say you have a model that wants to predict if the person should be admitted to college or not according to SAT score. And then humans, of course, trying to increase their SAT score either by studying hard or if they are privileged, they take the exam multiple times and submitting their higher score. If another example, if the probability of arrest is high without committing a crime for one group, then it's possible for the member of that group to become incentivized to commit crime regardless. Like this is usually happen in our lives as well. For example, for me, I use the GitHub Copilot all the time, and then GitHub Copilot is really good for older data structures like data frame, and it's not good for newer data structure like Hugging Face datasets. So whenever I work with a Hugging Face dataset, I first transfer it to a data frame. I do all my pre-processing, and then I transfer it back to the Hugging Face dataset. This is, of course, not optimal, but this is how the model incentivizes me to change the way that I code. So as humans change their behavior, then model change to fit the population. We all know about the A/B testing in the industry, which optimizes the model for the current users. And then this optimization may worsen the model over time for protected groups. This has been shown with some great papers from LinkedIn, but to just like give you an example, let's say you have a model that works well on average, but very bad for group X. Because it's bad for group X would leave the system. And then because group X leave the system, we have less data from group X. So next time that we update our model get even worse for group X, and then this loop happens again. Group X leave, less data, get worse, group X leaves, and then this feedback happens to the point that group X might not even use our system. For people who like a linear classifier, let's say we have 2 groups here, and then at first, like at time 100, we have this classifier for positive, black positive versus the red negative. And it's kind of fair for both teams, maybe a bit worse on the right group. And then if the right group start leaving because it's bad, over time, this classifier become worse and worse for the right group and just keep fitting the left group. And then after a while, it has like a very bad performance on the right group. So in general, any model that works with user feedback change over time accordingly, but machine learning make this process faster because it's really good on optimizing over many different features, and we do this rapidly every few months using the newly collected data. So with this, I finish my talk. As a conclusion, in business need, we should be careful about developer biases. Whose need are we addressing? In problem formulation, we should care about proxies, misuse, and what incentives we give to the people. In data collection, there are many biases that might present in our data, so it's good to think about it. Feature bias, label bias, distribution bias, and sampling bias. In algorithm selection and training, again, we should think about all these things that can go wrong with the training procedure. We have majority bias, simplicity bias, amplification, misspecification, and all these like unknown artifacts. For testing, what are the metrics we are using? How do they capture the performance over different groups? And we should think about our user base bias. For deployment, we should think about deployed population and deployed application. And in feedback loops, it's always good to think about how people change according to our model and how our model change according to the change of the people, and then how this feedback loop is happening. So tracking this feedback loop is necessary, and understanding how this feedback loop is affecting different groups is really important. Thank you very much. And if you have any question, I'm happy to answer through email.